One of the common things chemical engineers work on in practice is the separation of species from streams of fluids. And this is a process known as separation, and separation involves the use of mass transfer. And so I'm making this video to give an overview of the equations involved in a typical mass transfer problem you'd encounter in a chemical engineering class, and hopefully you find it helpful. So to begin with, let's say you're a chemical engineer working at a coal power plant, and you have a flue stream, an exhaust stream, exiting your plant that has a certain concentration of sulfur dioxide. And the EPA has regulations that say you cannot have more than a particular amount of sulfur dioxide exiting your flue stream into the atmosphere. Consequently, you will need to design a stripper, which is something chemical engineers use to define things that remove species from streams. In this case, it's a gas stream. And in this case, what we're doing is we're bubbling our flue stream through a column of water. And as these bubbles move through the column of water, the sulfur dioxide will diffuse out. And to take one little bubble and create some kind of concentration profile, what we would see is that in our gas phase, we would have a high concentration of sulfur dioxide, which I abbreviate as A, and that is leaving the gas phase and entering it by diffusion into the liquid phase. And so what we would expect to see as a concentration profile is something that looks along the lines of this. And so we can ignore these two terms here for a second. What we have in our gas phase is we have a downward slope on our concentration gradient. So the farther out, so if you look at a spherical bubble, as we move away from the center of the sphere, the concentration of A is decreasing until it gets to this interface. And once it gets to the interface, it reaches this particular PAI value, which is assumed to be constant. And so at the interface between the liquid water and the gas bubble, we have another concentration in the liquid phase, and that is also a constant value referred to as CAI. And so these two values, PAI and CAI, are constants over time. They are dependent on Henry's law. They do not change even as your concentration profiles evolve. So as these bubbles move through and PAG decreases over time because more and more sulfur dioxide leaves the bubble, PAI and CAI are going to remain constant. This and it's a relationship known as Henry's law, which I will get to later in this video. And then once the sulfur dioxide enters the liquid water, it diffuses, and then we have this bulk concentration within the liquid known as CAL. And so one of the typical questions you'd be asked on a chemical engineering homework is, tell me what the PAI, the concentration of, or the partial pressure of A at the interface in the gas phase, and what the concentration of A at the liquid interface is. And these values are very difficult to measure in practice, so we're going to have to use some math equations and apply a lot of our rules to, or assumptions, to get them. And so to begin with, we are given typically experimental data, which tells us that tells us essentially these ratios between the partial pressure of sulfur dioxide in a gas relative to the concentration of sulfur dioxide in a liquid once they've equilibrated. And so equilibrium is a key concept in chemical engineering. It is not the same thing as steady state. If something's in equilibrium, it is pretty much useless to chemical engineers. Chemical engineers work primarily with the steady state. But we will use equilibrium data to derive some values later on that will help us evaluate what PA sub I and CA sub I are. And so given this data, these ratios at various concentrations of the ratio between the concentration of A in the liquid and gas phase at equilibrium, we can plot the data and fit trend lines to it. Now, right now is an important time to introduce one of the key things to take into account when you're using Henry's law, is that Henry's law only applies to low concentrations of low concentrations, very dilute concentrations. Once we get to higher concentrations, the linear relationship between the concentration of a species at equilibrium between a gas and liquid phase begins to become nonlinear. It turns into an exponential. But initially, we can apply Henry's law to the dilute initial region here. And one of the things that we're going to do to find our PA sub I and CA sub I values are create these kind of dummy variables, PA star and CA star, because to generate an overall mass transfer equation, we need our units to agree. And if you simply said PA sub G minus CA sub L, that would be a false math argument because this is moles per liter and this is pascals, so they do not agree. What we need to do instead is define these new variables PA star and CA star as one of the initial steps to determine PA sub I and CA sub I. And just to give a little bit more background on what flux is, I think it would be useful to understand, well, we can think of flux as any flux in general, and we see this again and again and again in momentum transfer, mass transfer, electricity, heat flow. These are all common examples of when we can apply these flux equations to it. And so flux is some kind of resistance term times a driving force or some kind of transfer coefficient, driving force. So in this case, we are examining mass transfer between gas phase and a liquid phase. The driving force is the difference in concentration between the two phases. We know from physics and life that species will move from high concentrations to low concentrations. And then, so that driving force is what we plug into our flux equation. Our resistance term is equivalent to our little k sub L and little k sub G terms here. We can equate these two. So both these equations give us the number of moles of A that are diffusing per time, so per area. So flux equals moles per time per area. And you can, flux can be any quantity. In this case, we're using moles. So we can equate these two terms because we're assuming there's no chemical reaction occurring. All that's happening is the sulfur dioxide is diffusing into the water. So, and we're also operating at steady state. Consequently, our mole balance equation simplifies down to just flux. And what we know is that any molecules diffusing from the gas phase must also be diffusing into the liquid phase. The number of moles of A is conserved because we don't have any chemical reactions and we're at steady state. There's no accumulation. And when we do that, and we equate these two terms, we can begin to derive relationships for overall liquid and gas mass transfer coefficients. Given some equilibrium data, we can plot it and derive a linear, apply in Microsoft Excel or MATLAB a linear trend line to it and find the slope of that trend line. And we can use this information to derive what PA star and CA star will need to be. So that's the first step before plugging in or deriving your overall mass transfer coefficients for your gas and liquid phase, is to derive these PA star and CA star kind of dummy variables. Although they are dependent on so PA star is dependent on CA star, but they're not equal to each other. They're related in an equilibrium relationship, and this equilibrium relationship needs to be found by deriving the linear relationship between the partial pressure and the concentration of A in the liquid and gas phase. And once we know that, we can derive PA star by multiplying the slope of the relationship that we derive by the concentration of A in the liquid. So CA in the liquid in this case for this problem was 0.55 kmoles per cubic meter, which tells us that this PA star value is equal to 365 pascals. We do the same thing, except when we are deriving the CA star value, we instead take the pressure of the sulfur dioxide in the gas flue stream, and then we divide that by our slope, and that tells us that an equivalent CA star value in here is 7.53 kmoles per cubic meter. And I think maybe a interesting way to think of these PA star and CA star values would be to pretend if instead of having a different phases in our mass transfer, if we pretended that our gas was actually a liquid, this is what the liquid concentration of A would be, and vice versa for the gas case. If this was gas A and this other side was gas B, what would the partial pressure of A in gas B be to get the equivalent mass transfer? And so once we've derived these two special variables, PA star and CA star, we can go about finding the big K sub L and big K sub G values. These are our overall mass transfer coefficients for the liquid phase and the gas phase. And we can equate these again to the mass flux, because the number of moles of A that are diffusing are constant throughout. So number of moles of A diffusing at Z equals, we'll call this 0, are equivalent to the number of moles of A diffusing at this Z value, this Z value. For all Z values, the moles of A are going at a constant rate. It's essentially an assembly line, and there's no loss, no accumulation. So this is the reason why we can make these assumptions. And we can use some more relationships you can look up in a textbook that tell us that we can derive our overall mass transfer coefficient in our gas phase if we take the little k sub g, the k sub g value we used in deriving the mass flux, and that's typically a given value on a problem statement, and then applying this equation to it in addition to the liquid diffusion coefficient, not the overall, but just the liquid diffusion coefficient in the liquid itself, and that tells us K sub G and K sub L. So once you know big K sub G and big K sub L, we can go about actually deriving what the interface concentration of sulfur dioxide would be. And I'm sorry for being a little long-winded on this, but what we will do is we'll apply the mole conservation law to our two equations here, because the number of moles of A that are diffusing at any Z value are the same. We can make this relationship that big K sub L, the overall liquid mass transfer coefficient for A, times Ca star minus Cal. So we're essentially just looking at this line, pretending that our gas phase is actually a liquid phase, and we plug in our big K sub L value is times our driving force, which would be Ca star equivalent minus Ca liquid. This because we're looking at the overall. That must be equal to the same mass transfer that's occurring in this region here at the interface, which would be a little K sub L, CAI minus Ca liquid. And when we do that, we're able to figure out that our we can do some algebra and simplify our Ka sub I value, the concentration of A in the interface in the liquid phase, and we get a value for that, and then we apply the same logic to deriving what the partial pressure of A at the interface would be, and that tells us what Pa sub I is. So even though you couldn't measure it in practice, we can at least calculate it in theory. It's important for using these relationships when you're working with absorbers. And yeah, the final thing I'd like to note is we can talk a little bit about resistance. So resistance and mass transfer, this resistance term that appears in every single one of our transfer phenomena problems, this resistance term is proportional to the inverse of little k sub L and k sub G. And so what that means is the bigger k sub G is, the less resistance the gas poses to the diffusion of A across the media in the gas phase. So as the k sub G value increases, these lines in our concentration profile get sharper and sharper and sharper. And when they get sharper, saying it too many times, what happens is we get a larger diffusion, we get a larger concentration gradient in the gas phase, and because of that, the mass transfer through our gas phase becomes even quicker than it was before, which means that with higher K sub G and K sub L values, we get faster diffusion. So hopefully this helps, and if you're interested in chemical engineering and absorbers, hopefully you'll find this interesting. Thanks for watching.